Okay, so what is the aurora? The aurora, also known as the northern lights and the southern lights, is created when charged particles from the sun interact with Earth's magnetosphere, bringing them into the Earth, or ideally, in most cases, repelling it away from the Earth. But on stronger events, the charged particles enter the ionosphere through the magnetosphere's influence, triggering a solar storm. Where the charged particles interact with ions in our northern on the upper part of our atmosphere and create the colors that we can see. Green being the most common as an actual color. Typically for most people, they're black, or not black, they're kind of gray or white, kind of a diffuse thing. When they get stronger, you can see greens. If you're really lucky, like in May, there was one of the strongest solar storms ever recorded over Mother's Day weekend. It was, I think, the top 3 or the second strongest storm recorded. And through naked eye, could actually make out reds, purples, blues. The people that I were with, we were on the North Shore, were like freaking out, and they're also giant aurora nerds as well. So, and specifically, stronger stormy, you can see these colors with the naked eye. All right. So first, also, welcome to Solar Max. The sun goes through an 11-year cycle. This is the 25th recorded cycle. The solar cycle is just a measurement of how many sunspots. So if you were to look, during the eclipse, people get the solar filter goggles. You can look at it without damaging your eyes, like a certain president. And you can see these little black dots on the solar disk. The measurement of those black dots, the sunspots, are the indicator of where we're at on the solar cycle. More dots means more activity. That also correlates with more aurora, because those solar spots are what typically fire off solar flares, which push a bunch of particulate matter at the Earth. And we're right at the top of the cycle of solar cycle 25. So right now is a great time to be looking for the aurora, because it's the most active that it's likely to be in the next 6 months or so. It's kind of ambiguous when it starts, when it ends, as far as max goes, and then we start to decline a little bit in activity. But on the other side of the cycle, when it's going down, you actually see more aurora for the next year or so than you do the year preceding solar max. So we're in a great spot next couple of years for aurora chasers. Quick on just so I already kind of described a little bit of the science of the aurora, and we'll have a video that puts it in a little bit more of a visual for you coming up next. But you get these solar particles from the sun interacting with ions in our atmosphere. In particular, does this have a pointer thingy? Ooh, fancy. So green is what is most commonly seen in aurora in like middle kind of strength storms. When it's higher strength storms, we start to get the other colors, mostly because then there's so much more particulate matter in the atmosphere that is interacting at a higher elevation and a lower elevation. So we start at around so when it's the strongest, at about 60 miles above Earth, going up to close to 150 miles above Earth. So this is all very high. This is above clouds, obviously, and it's up in the upper reaches of our atmosphere. When the sun's particles interact with oxygen, we're getting green. Up here, a little bit more diffuse, we're getting some red, nitrogen lower in the atmosphere, producing purple and blue. So this is just why we see different colors as we see them during a solar storm. All right, and this is one of my favorite, it's very kind of basic videos. I pulled it down off of an account on Instagram, just explaining what the sun does and how the aurora reaches us.
Properly charged gas is called plasma. The plasma drives the magnetic field further outwards. The magnetic field stretches and twists like a rubber band. Then the rubber band breaks. Several billion tons of plasma is hurled out from the sun. This is called a solar storm. The solar storm can reach speeds over 8 million kilometers an hour. After 6 hours, it blows past the planet Mercury. The solar storm reaches our path. Something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
All right, so it's just kind of a basic of how the Earth's magnetosphere interacts with the sun's particles, giving us the aurora. There's two things I'm going to talk about for how we get aurora. One is a coronal mass ejection. So that, like we just saw in this, that video, is when there's a big solar flare and there happens to be a bunch of material that is shot off during that solar flare towards the Earth. That can create those can create the strongest, more pronounced visible aurora events. Such as during Mother's Day, May 10th through 12th, we actually had 2 or 3 nights, depending on where you were on Earth, of aurora from this one storm. It was so massive and so long-lived. The other type is a coronal hole, which creates high-speed streams. I'm just gonna. We don't need to watch this. Oh, okay. So this is just a video from that, just to see what it looks like when there's solar flares that are popping off and sending solar storms toward the Earth.
Towards the Earth, they're just going out.
They're happening all over the place. They're happening this way, that way, this way, that way. I guess I don't have a slide in here, but if you imagine the solar system is in a plane. It's a disk that all the planets are relatively aligned on, orbiting the Earth or orbiting the sun. So to have a solar storm reach Earth, the sun's a 360-degree ball, firing stuff north, south, west, east, west, compared to Earth. When something is in the Earth strike zone, roughly along the center of the equator of the sun, and rotated into view of the Earth, then it's going to send things toward the Earth. And as we continue to rotate around the sun, when we meet up and we hit it, that's when we get the aurora. So it's not always like, frequently there's a major flare over here, and that's the sun is rotating away from us that way, and we won't get hit by that. And I actually have a slide of, there was a CME, a coronal mass ejection, 3 days ago that was modeled to maybe just graze us, and we'll see a visual depiction of that. We didn't end up seeing it, but it shows kind of what happens when in a near miss situation. The coronal holes that create high-speed streams, these are more kind of predictable. The sun rotates in a 28-day cycle relative to Earth. So this was taken last December. There was this really pronounced, not 2 Decembers ago, I guess, coronal hole that again passed through the center of the sun's equator, both crossing north and south, so traversing the equator. So what happens then is that this is a darkened region visually, but it's a cooler and less dense spot on the sun. When that interacts with the normal hot areas, it creates a disturbance, and the sun sends off streams of solar wind at a higher speed and a little bit more dense in the particulate matter and more consistent. And the sun's just spitting that out as long as that coronal hole exists. So like right now, and I'll show you one of these apps, it's modeling at the end of this month to have a current solar spot rotate back into view and give us some enhanced solar wind. So right now it's a prediction of, which I wouldn't trust at all until it's more verified. About 21 days from now, we could have some aurora just based off of this. But a lot can happen on the other side of the sun, and that spot could collapse and it just doesn't materialize. But that's another way that we can get auroras. These coronal holes create fast wind coming at us. Yeah, this is just a video of the sun's rotation and showing a coronal hole moving into the Earth view. It's right there. All right, so how to predict the aurora? You cannot 100% predict the aurora. All the data can line up wonderfully, and we won't see it. That just happens. There's been countless times where I've been at my home in Eden Prairie and everything's looking good, and I haul it up to Ely, get to our cabin, and I'm waiting, and it's nothing. It's not all for nothing. I'm at our cabin, so that's cool too. But it'd be boring just to talk about that. So we're going to just talk about giving you the information now that we know kind of what the aurora is, how it's formed, on how to chase or how to find the aurora to the best of our abilities. Before I get here, so it's important to note too that there's only like 4, maybe 5 satellites that are monitoring the sun. for aurora kind of material. It's important for a variety of reasons. One is increased satellite communications and navigation. And now with the Starlink satellites for internet, there's a lot of reason to be paying attention to what the sun is throwing at us. Because when you don't, and this just happened last year, there's a major solar event. I think it was the Mother's Day one, where some of the Starlink satellites, the Elon Musk satellites, were pushed out of orbit and burned up in the atmosphere because they didn't take into account strong enough solar storms that could do that. So that does happen. And also astronauts on the ISS need to know because it's increased radiation they have to be prepared for. People that fly, especially over the poles, airplanes, if they do that frequently, if there's a solar storm, maybe they change out crews if they've recently been exposed. So there's a lot of reasons to pay attention to it. And it just so happens that we get to take some pretty pictures. The best times of the year are the equinoxes. I won't get into it, but when the Earth is tilted that way at the equinox, the Earth absorbs the material from the sun better. So March and September frequently have the most heightened activity for solar storms. And the darker months. Here we are in Ely. So this is just an example in the summer, this right along here. We're sitting between 15 and 17 hours of daylight in the summer. If you think of a probability standpoint, the longer it's darker, the more likelihood you're going to see the aurora. Compared to then winter, where we have roughly 8 hours of daylight. So like right now, we have much more dark time, much more probability to see the aurora. So both equinox, but then if it's in the summer when we only have really 4 hours up here, especially of true dark night, astronomical twilight, where the window to see the aurora is much shorter. Other factors, you want dark, like I just said, but cloudless nights. Clouds are the death of seeing the aurora. And it's not looking hopeful for tonight, though we don't have anything predicted anyway. Night, astronomical twilight and later. So when the sun goes below the horizon by about 12 degrees, that's when it's about the darkest it's going to get. It'll get a little bit darker, but that's really the darkest skies you'll see until it rotates around again, or I guess we rotate, and the sun comes up on the other side and starts to lighten the sky for dawn. Anybody who's a pilot is familiar with the various forms of twilight. But astronomical twilight and later is the best time. A new moon phase is important. A full moon could completely wash out the aurora. Although I will say in a very strong storm, half moon or even less can actually enhance the colors because our eyes don't pick up colors in the dark. You know, it's black or white that we see. When the moon is shining some light on it and magnifying the auroral phenomena, you can actually see more colors sometimes. So it's a delicate dance. Preferably, we like no moon though. And then, yeah, some new moon phase, and then also magnetic midnight is a consideration. So this is a picture of the auroral oval. There's a geographic North Pole, which is how the Earth spins on the axis, but then there's the geomagnetic North Pole, which is what the aurora cares about. This is the focal point of our magnetic field. And that's where that disperses the sun's activity around it in a concentric circle. Since it's almost directly south a bit from geographic North Pole with relation to Lake Superior, it's kind of a straight line. We in Ely right now are actually in one of the best places in the lower 48 to see the aurora, just because the offset from the traditional North Pole pushes the aurora down over Churchill and Hudson Bay. Just over kind of normal circumstances. But even in slightly enhanced solar wind, we get a good chance at seeing it here in Ely or in the Boundary Waters or Voyager, North Dakota, that sort of area. So lucky us, we live in a great spot. Okay, so that was the when to find the aurora. Now here's the how part. This is thanks to ChatGPT's AI. Just I'm not going to lie there. Okay, how to predict the aurora. I'm going to start with the KP index. I think people have heard of that. I want you to disavow any serious credibility put in KP, and I'll talk to you about why. We're going to go through KP, ovation. I'm going to kind of go sequentially of less reliable to more reliable data sources, and all these other things that we'll talk about. So the KP index, probably seen or heard this, is when media picks up there's a big solar flare with the CME associated with it, and we're expecting aurora. And the media typically is like, we could see KP of 8. KP is a measurement of the previous 3 hours of global activity. So 3 hours ago, it could have been really, really strong in Russia, and everybody's saying the KP is unbelievable. We're gonna have aurora tonight, and then it fizzles out and we don't see it. It's kind of an indicator that stuff is going on, but it's not going to tell you right now if you're going to see aurora. Also, if there's aurora overhead and it's been super strong for 3 hours but it's starting to die out, again, it could be like it's a scale of 1 to 9. If KP is 7, you're going to see it for sure, but it's already died out, and you're wondering why am I not seeing anything? It's a KP 7. Well, it's averaging the previous 3 hours, so it's not a reliable in the moment indicator. It's kind of a predictor and an explainer for people. Just an easy number scale of this is what could be coming at us. And so, for example, this was taken out during the Mother's Day storm. Sven Sundergaard wrote a thing about how KP index is 8.3 is forecast. No factual basis for that other than kind of prediction modeling. That's what it said. The Ovation Prime model. So this is also, we've seen this a lot on reports when things come out. This is was the model. This is the visual depiction of what the KP could be. So this is just explaining to you in a visual form the number system. It does turn out though that the predictions were correct because it was a massive, huge X-class flare, which is the highest class flare, that popped off, and it arrived, like the video said, in about 3 days. This one actually arrived in about a day and a half. It was about twice as fast as normal, and it slammed into Earth and rattled the magnetosphere for about 3 nights in total. And this is actually me on the North Shore, just outside, just next to, it was so strong, Ely was too north for it, had to go south. So I was with my friend who's the lighthouse keeper at Split Rock Lighthouse. And so we just went down to the beach and we're looking south at the aurora from a side profile view. If you go back to where the aurora oval was, where it's kind of centered over Churchill, it was so strong it was pushed. At this moment in time, it was located over Iowa and Nebraska. It was that far south and that far strong. The storm also created aurora images from within 10 degrees of the equator. So it was one of the strongest we'd ever seen. I had a friend who was in Tibet at the base camp of Everest, and he was seeing aurora down there. So it was a pretty wild storm. Second, so NASA and NOAA, the Oceanic Atmospheric Administration, both have 2 different models that they run when solar flares pop off, kind of predicting when in time it's going to hit. We're starting to get a little bit more reliable data now because they're taking measurements from all the satellites they have. They can measure the speed of the CME within approximation of how fast it's going to arrive at Earth, how strong it is, and they model it for where it's going to arrive. I'm going to let this play out, and it'll just keep looping here so I can talk about it. So this is the one that just went off that we were maybe going to see something last night, but we didn't. So Earth is the yellow line here. So this is looking top down. The sun, all the other planets in the orbital plane. Earth is right here. The solar flare and the CME popped off going this way, and it looks like it was just about to graze the Earth, though I didn't really see it happen. But it's a really good depiction of when this is rotated just a little bit, and if Earth was in the middle of that, then we're very likely to see some aurora. On this sheet that I have that's maybe looking a little bit daunting, I do have the link to find these, but also because you can't click on paper, I have suggestions on how to Google it to find it. So if you just Google NOAA Enlil solar wind prediction, it'll pull up this and you can see kind of what's coming. And it predicts out to, so the timing starts on the 4th and goes through the 11th, and they update it every few days with new information coming out. So it's a pretty good approximator to see what is coming, what's not. So this is NASA's. NOAA has something very similar. That's what, if you Google, you'll find that. It's a little bit easier to find than this one. Same general idea of you can see where the solar material is in relation to Earth, and it's a prediction model. So it could happen, it could not happen too. The AE index. So this is the one with the orange kind of squiggle on your page. So now we're talking about the CME has arrived. Everybody on Twitter and Facebook is, auroras everywhere, you should go outside. This actually is an instrument that can tell you if it's actually happening right now. So if you're home and it's cold and it's dark and you're thinking about going to bed, but you don't want to trust other people, you can actually look up here and you can see, is the data actually sound? So versus satellites, these are on the ground stations centered within the aurora oval. around the Earth, measuring at every single moment what the aurora activity is up to. Anything over 500 nanoteslas, that's the measurement here. I'll skip ahead and go back. Anything that's going to produce some that's considered solar storming, you're going to see this. So this was a time lapse I took on Easter Sunday 2 years ago. I call it Crown of Thorns Aurora because we got some nice little spiky points there, kind of in a circular pattern. I just like when data and real life coincide and prove each other out. So we had this great AE plot. I was at our cabin. I was looking at all sorts of information, and this started to really just build and build and build, and I knew it was about to happen. If we go back a little bit too, this is then a satellite image of what the aurora looked like at that moment. I just think it's really cool that you can see kind of the swirls here, and you can see the swirls here. So we get this profile view. Most commonly, we see the profile. If you're in Fairbanks, Alaska, you're looking straight up, and the aurora is like cascading down at you. In strong storms, that happens here too. The most common in Minnesota and Ely is to see the profile of it. You know, it was located, yeah, just south of Hudson Bay here. That's where it physically was on the globe. But we down here in Ely could look north and see this. Because again, it's like 60 to 130 miles above Earth. And so it's a true global event in the circumstance that we could see it, somebody in Maine could see it, somebody in North Dakota could see it. Obviously, people in Canada could see it. It's a pretty cool thing. Yeah, so that's the science kind of matching real life, which I always like. I'm going backwards by accident. No, okay, the ovation. Oh, I meant to keep that as saying AE, but I didn't update it apparently. This was the AE plot for the big Mother's Day solar storm. So the measurements were literally off the charts. There was so much activity and so long-lived and so dense and so powerful and fast that the measurements couldn't, at least in this graphic system that I here, keep up with exactly how strong it was in that moment. So like this is much more typical what's on the paper. When you get these once in 100 years or 3 times in 100 years solar storms, this is what it can look like and what it looked like this previous May. Okay, now I'm going to talk to you about this one app that's my favorite app to use called Space Weather Live. And I have it again listed on here as on point number 3. So say the solar storm is going on right now and or you're waiting for it to come. What is it you can look at? So you open up this app and it has several things to look at. One is just the KP index again, throw that information away, other than it's kind of like, yeah, there's some stuff going on. The things to pay attention to primarily are, well, the first one is BZ. So BZ is the polarity of the aurora's material. A southern pushed polarity means it's being pushed away from the North Pole and south. The more south, the more negative this number is, the better we are here in Ely to see it. If you're standing in Churchill, Fairbanks, Reykjavik, you're going to see the aurora pretty much every night just because that's where in latent phases of the sun, it's always just cascading. It's in stronger events where it pushes south, as indicated by the BZ number, that we have more likelihood to see the aurora. Starting about -5 is a good number to think about. You might see it on the horizon in Ely. So that's the first thing to look for. Other thing, and that's the main thing. Other things that are important, solar wind. Once you start getting up to 500 in solar wind data, you're likely to see something. Density, this wasn't very dense, but you want to see the density go up. This is in between 2 and 4, getting up into 5, ideally more than that. You're going to have thicker aurora. It's going to be brighter, more compact, and produce more light. And then the magnetic, this is just kind of amalgamation of everything else, just kind of the overall strength. So primarily, this is the one to look for. You could have super strong, fast solar wind, high density, but if this is north, all that aurora, the material is being sucked toward the North Pole, and we probably won't see it here because it's just localized too far away from us. So you want it to be southern facing. And again, that's on the sheet. The Space Weather Live app. You can get on iPhones, Android, probably other phones, I don't know. Okay, so now my secret tool of when it's going and how you can tell how the aurora is going to act in live time. So there's these things called, so this is a band or an arc, kind of same names, where the aurora is relatively compact and defined. What happens is, like when we saw in that video, all the solar material kind of goes around the Earth and it stretches the magnetosphere like a rubber band. And when it snaps back, then this turns into something more like that, where it just diffuses throughout the entire sky. That's called a substorm. That's where if you've seen the northern lights, you've seen like pulsing in the sky, that's a substorm. That's when the rubber band breaks, sends all the material rushing back at Earth, and you get it spreading throughout the sky. So this is called the GOES. I don't know what GOES stands for. It's probably on the website. Magnetometer. These are 2 satellites stuck at geosynced positions relative to Earth on the North American side. One satellite is on the west coast, one satellite is on the east coast. And when it rotates to the dark side of the Earth, it starts picking up what that magnetic tail is doing. It doesn't really matter to us what's happening during the day because we're not going to see it. But at night, when it's now dark time, we can see the aurora, it's going to start showing you this graphical depiction of when the aurora is loading and when it snaps. And I didn't have a super great example. I'm a big Lord of the Rings nerd, so bear with me. Okay, so here's explaining this. This is daytime, this is nighttime. So during the daytime, or maybe this is nighttime, this is daytime. When the satellite rotates, so a normal curve when nothing's going on is just a regular sine wave, going up and down. During the daytime, there's not a lot for it to read. At nighttime, that's when it travels through the magnetic tail on the dark side of the Earth, and it's measuring the data. When there's more activity going on, it gets disrupted. So this was January 1st, just a few days ago. There was aurora. It was cloudy here, of course. So we couldn't see it, but if you were in a plane above the clouds, you would have seen something. What this shows is when it's in a loading phase, the lines are going down. Blue is East Coast, or like Alaska. Red is blue is West Coast. Red is East Coast. We're obviously in the middle, so you can kind of look at both of these. They're going to mimic each other. So the point to look for is in a normal sine wave, when suddenly it goes down and snaps up, and then goes down and snaps up, and goes down and snaps up. That snapping up is when you have about 5 minutes notice that the aurora is going to explode above the sky. And that's a really cool thing because there's been times, and I think I have a video of, I don't want to watch that again. Hold up. Okay, so this is my favorite GOES moment, GOES magnetometer moment. I had paddled into the boundary waters from a cabin. I was getting cold and tired. This is in November. And I had taken like 1,000 pictures that looked exactly like this. I was like, I just want to go. But I pulled up the GOES thing. I was watching, and I saw the band suddenly snap up. And you'll see this in live time on this time lapse here. So right about here, I'm getting tired. I've taken a lot of these pictures. They're beautiful, but I'm just kind of bored with it. Suddenly, right about now, it snaps up, and you'll see the aurora starting to load. So it's going, now the GOES plot is going down, down, down. We're getting more characterized aurora here. And then suddenly it just goes poof. And that's the line snapping back up again. So it's a really, really cool way in the middle of a solar storm to tell if you're about to get an extra show. In a strong storm, there can be about 3 of these events where the aurora, the energy is loading and then releases, and then loading and releases. And it can do it several times, but there's kind of like big ones that really just impact the Earth, and it shows what this is going on. So again, this is 4B on your sheet here, the GOES magnetometer. You just Google GOES magnetometer or carefully type in the entire link, and you can find that. I have it bookmarked on my phone, so when I'm out watching the aurora, I can see what's happening in live time, and I know I'm getting tired. I'm going to go in, and I'm packing up my camera equipment, and suddenly it snaps back up. I'm like, oh, okay, get stuff out again, see it. In August, I just have an anecdotal example. It was another really, really strong solar storm where it was localized over the metro, and it was cloudy up north. So I actually took my kids and we went south to south of Northfield, and we were looking north from Northfield, and we had missed kind of the main impact of the CME hitting, and we were kind of bummed because we just didn't get out on time. And we were driving down anyway, just getting into position just outside of, just south of Northfield. We were literally in a cornfield. I'm just kind of waiting. And we're getting some cool pictures because there's still stuff going on, but the kids were getting kind of tired. I had to drive back, and we're about to pack up, and then we saw it just spike up again, and we got this amazing display, and we were just very excited about it. So this is really like one of the most powerful tools in the middle of a solar storm to tell what is happening almost immediately. Within 5 minutes of that line going back up, you're going to get that expansion. Okay, so this is all the very detailed things. If you're a giant nerd and you spend 5 years memorizing how this all goes, and you've got it committed to memory, and you've got all these bookmarks, and you've laminated this, and you take this out in the field with you, and you know exactly what you're doing. If you're not that sort of person, I've got some cheat codes for you. The first of which is live webcams. This makes it incredibly easy. So you can be in your bed, you're in Ely, you hear this aurora is coming, you maybe want to go out, maybe you don't. Just check one of the live cams. I'm starting with Maine. So if Maine is seeing it, anywhere in Maine is more south on the latitude scale than Ely, Minnesota. If Maine, and it's further away from the aurora oval. If Maine is seeing it, we're going to see it. So you can look at this up. Again, I've got. Oh shoot, I didn't include in the paper. I think Lacey sent stuff out. You can attach this. So there's an observatory in Maine that's pointed north and is on all night, and you can pull that up. It's midnight there. It's 10 o'clock here. You're thinking, what do I want to do? Do I want to see it? I guess it's 11 here. And they're seeing aurora, so we're likely to see it as well when it gets dark enough. The next couple best ones are just right here in this area, and Gunflint has a all sky camera, and you can just load that up, and if they're seeing it, we're definitely seeing it here. If it's cloudy there, you could check the Isle Royale north facing webcam and see what's going on. Lake Superior, as we all know, has really weird weather. It could just be socked in with clouds on land, but clear skies in Isle Royale. So just out of excitement or interest, you could see if there's aurora, even if it's cloudy here, or if it's cloudy in the Gunflint, clear here, and Isle Royale can give you an idea. And then also there's a live cam in North Dakota, just another kind of a close-ish by area. It's usually drier and less cloudy there than it is here. It's kind of on average. So usually more clear skies that you can see, you can tell. So if you want to just watch these, you can forget everything I just told you and check the webcams and you'll be set. The other one is social media. Follow me, I'm a giant nerd. When there's aurora, I post it about it. I plan to do so when I'm in the legislature too. There is a nerd caucus at the legislature, and I'm between this and Lord of the Rings, and I qualify. So I'll be a part of that, and I'll be posting a lot about it. This is my friend who's the solar physicist who lives in Fairbanks. He's getting his PhD. He's made his life's career, literally, about the aurora. He also runs out of Fairbanks aurora chasing tours, and he has a couple staff working for him. Where if you go there, you can pay them and they'll cart you all around to find the aurora in Fairbanks. Tamitha Scobb, this is one of Vincent's former professors. She works somewhere in California, but she's a solar physicist and is always clued in on what's going on with the sun. And then Hayes Scriven, he's the lighthouse keeper at Split Rock that I just happened to bump into. We were just outside, both driving up and down the North Shore, and we just kind of hit it off as friends. And we've chased the aurora quite a bit. The last solar eclipse, we went out to we traveled out together with our families to go see that. So he's always posting amazing pictures. If you want your social media feed to have a lot of Split Rock Lighthouse and the North Shore, and not politics, nice stuff to look at. But then also he's very clued into where the aurora is and what's happening. And aurorasaurus.org is a citizen science-based website where they take reports from people seeing aurora and then publish out alerts saying like people are seeing it. So if you sign up here, you can get notifications pushed to your phone. And mine is centered for Ely for obvious reasons. And I'll get a text at 10 o'clock at night being like, it's Ely, you have a 15% chance of seeing the aurora, or you're likely to see the aurora right now. So it's a pretty cool resource right there to go sign up, create an account, and it'll send you alerts based off of your location if you're likely to see the aurora. And if you do, you can send in a report to them that helps their whole data collecting, because then they compile people's reports with what the data looks like, all these metrics I've been explaining, to help refine what our prediction models are. Where to go to see the aurora? you want to have a dark sky. We've got the dark sky sanctuary just over there, just outside of Ely. So just heading out the Fernberg, you leave the very small light pollution bubble of Ely. My cabin is right there, so I'm sitting pretty. And Fernberg, the Echo, just kind of obvious roads, but I like to show this to other people too, so if they're in Ely, they know where to go. Just out the snowbank or wherever they want. Contrasted with where I live in Eden Prairie, it's relatively a disaster if you like a night sky. All right, so what does it look like naked eye compared to the camera? So like I've said a couple of times, our eyes are terrible at night vision. If there's any light, we typically see it just in a gray and white scale. So this is kind of just an example of what it looked like from my memory of what it looked like to the naked eye compared to what my camera picked up. So what I was looking at from what I saw, this was a very bright, very defined, compact moment of the aurora. This was before the expansion. So it was very defined and intense. I had my Nikon, I have a mirrorless Nikon. This was a Z6II or 2. There was a 5-second exposure at 5,000 ISO at the f-stop of 2.4. So those are the settings that I use on my camera to get this picture. I personally think it's a little overexposed. I could have bumped the ISO down, the 5-second exposure down, but I was also setting up a time lapse, and you can only just pick one setting and just let it rip all night. And so if it's dimmer, it's going to be underexposed. If it's super bright, it's going to be overexposed, and then that's where Photoshop comes into play. You can even stuff out. That's what I just explained. Oh, and also just kind of, for example, so when we're talking about a 5-second exposure, the human eye is a shutter speed on average of about 1/75th of a second. So when I'm talking 5-second exposure, that's about 350 times more light entering the camera, all that data layered into one image than we see in real time. So that's why people are like, I see all these beautiful images on social media, but when I go and see it, all I see is like a white cloud. Well, that's because our anatomy sucks. But that's what we got. That's why we have modern technology. That's also why people are talking about how with the Solar Max and people, there's like the aurora is so much more visible. Like it's never been like this before. Well, it's always been like this, always in this cycle. It's just now with modern technology and social media, with all this information at our fingertips, literally, that it's becoming a bigger thing. People are posting more and showing what the aurora looks like. But then it's also leading to people being misled on what it looks like in real life, which for what it's worth, but also aurora photography is an art form, and it's up to the photographer to kind of dictate what they want to show. And there's various tools. All the light is there. It's not like we're making it up. It's just picked up in a different way than our eyes can see. And then again, just kind of explaining here, 5-second image, roughly 370 times more light in one image than what you see with your eye. Camera setup. So any modern smartphone can see the aurora. If you've ever been out, you can hold it up and you might start getting a little bit more colors. I just found out a new trick. If your iPhone, I only know about iPhones because what I have, maybe Android has this too, but if your iPhone is in a stable location on a tripod or something, your night vision can actually go up to 30 seconds. I didn't know that. And I did test it out. It's kind of cool. Normally if you're holding it, the max you can get is 10 seconds because like you're too shaky and then it's going to be all squiggly. But you can get up to 30 seconds. But aside from that, both DSLR and mirrorless cameras work great. Mirrorless is a newer technology, but DSLR is roughly the same thing, just in different form. What you need, a wide angle lens. 14 millimeters is ideal. That's going to give you a roughly in the 200-degree angle sort of view. So you get much more wide of the sky's view than just a standard 60 millimeter camera where you're getting that nice square. This is a wider view. 20 millimeters is good as well. These are just kind of typical specs you'll see when you're looking for a wide angle lens. Nighttime settings, ISO 5000 is kind of typical. That's like the average. You can go lower if it's super bright, higher if it's dimmer to pick up more light. But 5000 is a good place to start. The aperture, you want to have the aperture as wide open as possible. So if you don't know cameras, that's the ring that's letting in the light. The aperture can open up or close down. You want it open as wide as you can. A little bit counterintuitive, wider is a lower number. So you want to have your camera settings at the lowest aperture you can. That means it's widest. And certain lenses have different lowest aperture settings. 2.4 is fairly common for wide angle lenses, but if you can get one, forward one, you want one in the 1.4, 1.8 range, you'll just get more light let in. The advantage of that is you get more light. The shutter doesn't have to be open as long, so you can get more definition in the aurora. The longer it's open, the aurora is undulating and moving, and it'll kind of become more diffused. So if you have a wider aperture, you can create more of a snapshot and get more of like the structure of the aurora. Again, all artistic preferences. A long exposure during bright intense storms, 2 to 3 seconds is fine. But you'll need to experience a lifetime for whatever you're seeing. Dimmer, you maybe go up to 10 to 15 seconds. That'll be a way to really pick it up. In that sort of circumstance too, in live, you're just gonna see kind of a glow on the horizon. Setting a camera up for 10 seconds, 15 seconds, now we're talking like almost 1,000 times more light than our eyes see. You're gonna see a lot more of the aurora. That's pretty cool that you just know it's there. You didn't see it, but yeah, you got a cool pic. All right, too long, didn't read version. There's 2 apps, and this is what the paper is. The 2 apps you really need or want, I didn't show it, but there's one called My Aurora Forecast and Alerts. That gives kind of a basic view and it's easier to see. It has a prediction model of when you're gonna see day by day, the likelihood of aurora. And it's marked in KP, again, whatever, but that's the prediction model of this is what at a 3-hour average, what the strength of it could be on that day. So that's just a good one. The one of the websites, like I just said, is the visual modeling where you can see the aurora as it is coming at Earth based off of the data that the satellites and the nerds at NOAA have compiled for us. Also this, modeled for storm arrival. Also has some of the current solar wind, like I showed the Space Weather Live. This also has some of that. So this is a good kind of just general. If you want to go just a little bit deeper, the Space Weather Live app, you can get more detail, and it's within 1 hour notice. And I forgot to point that out. If you're going to use that app, it makes sense that you want to know how to use it. So this line right here is where Earth is. The data is coming at us, moving right to left. So this is all in the past. This has already gone by. This is the measurements that are recorded and gone. This is what's coming at us. Because it's based off of a satellite, the Discover satellite that according to this, was about 50 minutes away from Earth. So everything we're seeing right here, we will experience in 50 minutes, which is pretty cool. It's another way to be like, I'm tired. Oh, but in an hour, it's gonna get good. So you can think about whether or not it's worth it to you to go out. And right here too, so right here, negative BZ, we've been sitting pretty for a while, but in 50 minutes, it's gonna go back north and we're probably gonna lose the aurora. So this is kind of the timeline. You can think, oh, I've got about 20 more minutes of auroral activity, then it's gonna fizzle out and I might as well just go inside and go to sleep. And then tell my friends how awesome my night was. So that's how, so this line is the thing to pay attention to as far as timing. And that's why this is a pretty cool app, because you can see 50 minutes into the future based off of what the satellites are telling us. And back to where I was, we're almost done. This is just a quick video of my favorite live video of aurora I took that was in Alaska. This was at the foot of the Brooks Range north of the Arctic Circle. It was negative 30 degrees air temperature, but I was super excited. The frame rate is about 1/40th, so it's a relatively smooth video. Moving on, this is just one of my favorite pics of the kids and I just outside of our cabin, standing in the ice, watching the aurora. Shortly after this, the GO thing went pop, and everything went up overhead, and we literally just laid down on the ice watching the sky just kind of pulses like we were watching the sky breathe above us. It was absolutely magical, and the kids still talk about it to this day. And they've created 3 new aurora nerds. And this, I just think it's funny because I spent 4 hours one night during this really intense storm trying to get what is currently my favorite picture. I wanted to have this to the Benny Hill music, but I didn't have the time. But this is just me paddling out, trying to stage myself just off of our dock, looking at the aurora, trying to get the picture I wanted. Many, many, many times. And then this is the result that I got that I'm pretty excited about. It was annoying. There was just slightly enough wind. You can kind of see it's a little bit ripply here. So I couldn't, it's me and my 3-person, I'm in 3 here. just acts as a sail, just kind of slight wind, but blowing me. So it was a challenge to just get set in one spot and be relatively still. But I like that pick. That's it. So I would love to entertain any questions.
Quick round of applause for Alex.
Yeah, and so like I said, just quickly before, I tried to digest the information I gave you in one sheet, so I wouldn't expect anybody to remember all this. And gave some visual descriptions or like of the AE index, what to look for, as well as in the goes, kind of a quick, but and then it's described there too. And I verified, I did Google each thing to see if I was pulling up the right data. So where here it has the website and I say Google AE index aurora, it'll pull up that website.
I recognize some people might need to leave. We'll go over a couple minutes. I think, is that okay? Okay, great. For Q&A, I just want to say I'm officially gonna rethink how I use the word amateur.
How high does the aurora sit? Like what elevation or what? Like I'm wondering, like when I flew through it, like was I looking to my side or above?
Yeah, if you're flying in an airplane, you're looking at it from the side, you're still below it, but you're high enough for your perspective from an airplane is a little weird because you're above, where you can see the curvature of the Earth. And if it's still far away, it's going to look kind of at eye view, but it's still significantly higher than what you are. It starts at the lowest floor is like 60 miles above Earth, for example. Reed?
Have you ever heard the aurora?
All right. This is riddled with controversy. People talk about hearing the aurora. No, I haven't, and I don't believe personally that people do, but perception is reality. If somebody thinks that they did, then sure, they did. But the science doesn't verify that. There's very, very fine-tuned, highly powerful microphones that people have been putting out to try to see if there's a sound for the aurora, and there's not. Generally, what people are reporting in is they were probably during a really strong auroral storm, and they were next to a power line or a transmission line or a power box or something, and they make sure they're out there during the day just doing whatever they're doing, but at night they were hearing it sizzle. They're perceiving that as the aurora. There's other reports of people out on the ice and they're hearing the lake kind of cracking and booming, and they just assume that's the aurora because they're very excited about what's going on. So no, I haven't. I don't think people have, but there's enough people out there that say that they have, but the science doesn't verify it.
We were flying over Greenland one time, jet, and the aurora, they were all multicolored. Why would they be, like you said, they wouldn't be the multicolors through the human eye?
So that's probably in a very strong one. So like in the Mother's Day storm that I was showing, like I was picking out reds and pinks and greens and blues and purples. It was the strongest storm I've ever seen, including when I was in Alaska and that was a solar storm event and it was like right above me. This was the strongest I'd ever seen. So that's why. Also, you're up higher and you're like closer to it, so it's going to be more vivid. You're also higher in an airplane and there's less atmosphere getting in the way, so less distortion or diffusion through molecules in the air. So there's a lot of reasons, but mostly because it's probably a very strong one and producing the colors that your naked eye could see.
Hi, the geomagnetic north moves relative to the North Pole. What will that do to viewing the aurora around here?
That probably means in about 7,000 years, Russia will see it more than we will. The last time that it flipped was about 22,000 years ago, and it has been moving. It's a very gradual process. And when it does do a full flip, there's then about a 4,000 year variation. We know it's because of ice core samples and the radiation that's embedded in the ice. And so when they've studied that, but it's a very slow process, incredibly unlikely to happen during any of our lifetimes, unless you're incredibly lucky. So it won't mean anything for us as we know it, but our ancestors' ancestors may have a different experience.
I was wondering if you use binoculars, is that vision like the ghost, or would that pick up the?
That's a good question. I would not use binoculars because that's going to just zoom in on a smaller area. And what you're going to see is what you're seeing from afar. You're just going to see something diffuse a little bit closer. which is why I recommend having a wide angle lens. There's people, they've done kind of like artful zooming in with a camera on a segment of the aurora and just filling the image with just like the streaks of the color. That's probably what you would see with binoculars. You would just see whatever you're seeing just closer up. And so I like personally to have the wide angle lens where I get the landscape along with the night sky above it and the aurora as well. Then that's just my preference.
This is a little different, but I've seen a really bright star by our moon. You know what that bright star is?
By the moon, typically that's Venus or Mercury. If those are, if it's within, you know, because they rotate and the moon moves and we move, the sun moves. But a bright star right by the moon is usually Venus.
Okay, because I'm looking south and I always think the North Star is really bright, but that North Star should be north, but
Yeah.
I'm looking south.
Yep, yeah, so it's a planet, most likely Venus.
So question, is this something like the space station actually is able to pick up that with Northern Lights?
Yeah, there's some really cool pictures from the space station where they're seeing it from above. And as they kind of go over the poles, you see the aurora and all of its activity. And they've got same cameras that we do. And so the astronauts are up there and they're taking pictures of it in time lapses, and there's some really cool stuff. So if you just Google ISS aurora, you'll see some pretty neat pictures and videos.
Do you know of any atmospheric factors like humidity that would make a difference in the aurora?
Only in how we see it. If it's a really humid day. So like, you're all Eliites. When it's cold in the winter and there's less humidity in the air, the stars just look so much more crisp than in the summer when there's more humidity. It'd be the same. It might not be super noticeable, but it could be. If it's a really humid evening and you're looking at it, it could just be a little bit more diffuse because the light would be reflected through all the water in the air.
I'm just curious, like you're so self-taught in this journey. Like, is it truly just intrigue and passion that help you persist through years of like getting such in-depth knowledge? Like,
Yeah.
what advice would you give someone who wants to be the level of nerd that you are? Said with all due respect.
Well, they say something, no, and I appreciate it. And nerds, thankfully, you know, nerds are ruling the world these days. There's the saying of to be a master of something, you have to do it for 10,000 hours. It's playing violin or being a chess genius or whatever. It's just repetition over time. You know, every time there's an auroral event, I'm looking at all the data and it just becomes kind of second nature. And then I have a question, I'm like, oh, what is that? And I talk to Vincent or just look up online more explanations and just uptake that knowledge over time. So it's really just been kind of at this point, a decades-long pursuit and just layering information on top of information.
I think that's just so powerful as a reminder if you are passionate about something to just keep going.
Yeah.
Like, I just think it's so cool what you can learn even on a self-guided journey.
Because of this painting class.
Yeah.
I'm just curious, and maybe you answered this already, but you know, there's so many variations in the way that they look.
Mhm.
You know, they have the ones that are like bands going across and sort of dancing like this. But then you do have like that one you had on the screen, that swirling one. So what is it that causes that kind of variation?
That is a great question. So if I were to hazard a guess, it's basically the strength of the aurora, how strong it is. So then it's kind of like if there's more just stuff in the ionosphere, it's going to be interacting and intermingling with itself because all the ions are charged and they're like negative and positive charged. You think about taking a magnet, putting the two positive ends, you can't squish them together. That's what's happening in the magnetosphere and the ionosphere. So yeah, so I'm not sure why. So there's all these different phenomena. There's one called the cinnamon roll aurora, which is relatively known. People call it that when they get that kind of swirly thing. I guess I don't know why. Just that it's cool that it exists. There's some other phenomena. There's one called Steve. If you know any Steves, there's an aurora named after him. Where so if the aurora is north, typically there's this phenomena, and it's relatively rare, where it's either directly north of you or a little bit south. And it's a single band, sometimes two bands that kind of look like it's braided together that flow together. And then it's also characterized by, it's called the picket fence, where there's these green streaks just below it. And I have a picture of it I could show you on my phone. that happened 3 years ago was one of the most notable examples recently. And so there's different things that happen. And one of the things that I really like about solar information research and aurora is that it's a relatively new scientific field, and a lot of it is unknown. So it might not be known why there's cinnamon roll aurora. The Steve phenomena has only been proved out because people with modern technology took pictures of it. It was so rare, people would be like, I saw this thing, and everybody else is like, no, you didn't. But now we have pictures that prove it. And then it's been shown that when that happens, and they look at the data, there's this other thing going on, and there's a defined reason that Steve happens. And there's other variants of Steve as well. There's SAR arc, another thing. I could go far too long to say names and nobody's going to remember or care about. But yeah, so kind of another explanation for your original question. There's a lot going out there. This is all relatively new science. There's not a lot of money to be made in studying the aurora. So there's not like an financial incentive to know about it other than it exists. And if people are passionate about it, they kind of make it their thing.
Well, thank you for sharing your passion with us, Alex. It was so great to learn from you.